Welcome back on Electrical Engineering 2, and then we gonna carry on our problem solving, and now it's gonna be under exercise 1.2. And so far, as you know, we have introduced already exercise 1.2, which is all about the parallel impedance. We have explained already what is an impedance and what to expect when everything's in parallel. Everything is the same as the electrical one, but here we are dealing with everything in complex form. So we are going to have a look on under exercise 1.1. We're going to solve question 1, question 2, and as well question 3. Because example they are made for you, you can try to understand them yourself, and if you have a question on them, you can always ask it. So what we are going to keep in mind is that in this question 1, they give us a parallel circuit that consists of 3 branches. So you can see that on my branch, I represent them. I put the 3 branch, and in each branch there is a current that is flowing as it represents on the picture. Okay, so we have the current I1, I2, and I3, which is the same as the current IA1, IA2, IB, and IC. Okay, so those currents were given in instantaneous value, so we need to change them to RMS. We are doing in this form. We change them to RMS. We change them to RMS. Okay, and the voltage as well was given in RMS, but we gonna in instantaneous value we're gonna change it to RMS as well. But remember, in a parallel circuit, the current is not different, which means the current that is going into a junction, this one is going to the junction, is going to be equal to the sum of the current that's going away of the junction, which means you have these two currents that are going away. So you just click off junction rule. So that's how we are going to apply in order for us to get our supplier current. Okay, so you can see that everything, the concept, the calculation is the same as for electrical one, but here we're just dealing with them in complex form. And then we were asked to calculate the total impedance. Therefore, we apply our Ohm's law. What is our Ohm's law? We know already our triangle, whereby you have your impedance, current, and as well resistor. And now we were asked to calculate the total impedance in the circuit. Then we apply our Ohm's law here to get the total impedance of the circuit. And when it's come to the 1.3, they ask us to calculate what's going to be the power factor in the circuit, and it's also straightforward. Remember, we have discussed already about this. We take the angle of the total impedance, that's going to be our power factor angle, or either we're going to take the angle of the voltage, which is 0, okay, minus the angle of the current, which is that. And if you apply the two-way, you're going to get the same answer. So as you can see, everything is just simple and straightforward. Okay, so we're gonna try again to have a look on question 2.2, question 2, and see what's gonna happen in question 2. But the concept is the same. Okay, and remember, in our previous video, they give us a coil, and I've told you already what is a coil. A coil is always a combination of a resistor and an inductor. That is what made a coil. Okay, so they give us a coil which is in series with a resistor. So you should be able to draw your circuit as well, which means when they give you some components, you should know that this one is in parallel in series, the same as the one that was given to you under your practical, but the concept still the same. But now we are dealing with them with impedance. So we can see that they give us a coil which is in series with that resistor. Okay, and they say this branch now is connected in parallel with a series of what? A capacitor and a resistor. Can you see? So you have them in parallel. Okay, and then they give us as well our supplier, which was given, and they say we must calculate the total impedance. So remember, we say when you have to calculate total impedance, everything should be in ohm value. So you change this inductor to inductance, and therefore the Z1, which is going to be the impedance in this branch, the impedance in this branch, the impedance in the branch is going to be R. Remember, you have two resistors, this resistor plus that resistor. Okay, this resistor plus that resistor plus J of XL, and that's how you get your XL, X1. Okay, which means the calculation that you did is just to get the total impedance of this branch, and then you can represent it in form of a block. Okay, And then you do the same for Z2, which is mean the second branch. And then you can see that in that branch we have an inductor, we capacitor, we change it to inductance, and therefore Z2 is gonna be R minus J of that. We have explained already how to get this, and therefore our total impedance is gonna be the parallel of what Z1 and Z2, so that you can get your total impedance. We were asked as well to calculate our value of the current that is flowing in the two branch, in the capacitor and as well in the inductor. Okay, so you know that the voltage in a parallel circuit is the same. Okay, so if I have a 220 volts here, I'm gonna have a 220 volt there, and I'm gonna have a 220 volts here. Okay, so I'm asked to calculate the current that is flowing in this capacitor and in the inductor, in this capacitor and this inductor. Can you see? But before I have to calculate, I need to know what is the total impedance here, so that I can apply Ohm's law to get the current that is flowing in this branch. And in this branch, in this area, which means the total current is this branch is gonna be the current across the capacitor. The total current in this branch is gonna be the current across the inductor. Simple and straightforward. So you go there here, you apply your Ohm's law, you calculate your I load, I coil, the current in the coil, which is doing the impedance Z1, and the current in the capacitor is the impedance Z2. And then now in 2.4 they ask us to calculate the voltage across each component. Okay, so what is a component? What is a component? What is a component in a circuit? Okay, so we need to identify what component we have in the circuit, and we can see that we have a resistor, we have a capacitor, we have a coil, because this coil is also a component, and then we have a resistor. So when we have to apply Ohm's law to get the voltage drop across this, I need to consider the current that is flowing in this branch. Can you see in the capacitor? I'm gonna apply Ohm's law with the current in the capacitor, and then here for the coil. So simple and straightforward. Again, we go down, we can do our calculation of this question. So for VZL coil, as you can see, it's gonna be the current in the coil times Z coil, and then you get your answer. For VR, you applied again Ohm's law, IL times R, you put it, but remember a pure resistor is always at the angle of 0. Okay, for VC is gonna be IC times XC, and then you take your IC, but remember a pure capacitor it's always at the angle of minus 90, and when we say pure, it's only when you are focusing on the capacitor. And then you do the same for the resistor, and then you're gonna be that, and the pure resistor is always the angle of 0, and that it, and straight and simple, straightforward, as you can see.